Okay, in this video, I want to walk through some of the simulated nFET 01V8 and pFET 01V8 characteristics using the models in the Sky130 PDK, and try to draw out some of the implications of those characteristics for circuit designs. So what I'm showing in this first plot is in all of these slides, the red circles and point markers represent nFET characteristics, and the blue circles represent pFET characteristics. And I have flipped the pFET characteristics around so that they will look very similar to or analogous to the nFET characteristics. So here we're plotting saturation current as a function of the gate to bulk voltage for the nFETs and as a function of the bulk to gate voltage for the pFETs. So that these characteristics, which would normally either be shown using like negative gate to bulk voltage or maybe down from VDD or something like that, which is 1.8 volts here. So they'd be mirrored horizontally, are shown so that they're directly comparable to the nFET characteristics. And so I'm showing you two different device sizes. In both cases, the drawn width and lengths of these transistors were going to be 3 microns wide by half a micron long and 3 microns wide by 3 microns long. So that's the same for this one. Here, this is 3 by 0.5, and this is 3 by 3, this one down here. And so you'll notice a couple things right away. First of all, the NMOS curves or nFET curves are shifted pretty far to the left here compared to the pFET curves. And that's a result of the threshold voltages being quite different for these devices. So for the NMOS transistors, the threshold voltages are around 0.5 and 0.55, 0.6, that kind of number, volts. And for the pFETs, they're up near 1 volt. The threshold currents, which is represented here on the simple EKV model by basically the strength ratio, which is the W over L ratio times IS, is pretty comparable for the N's and the P's. It's a little higher for the N's, so here we got 4.28 microamps versus 1.82, and 647 nanoamps versus 292 nanoamps. So, the N's are a little higher in terms of their threshold current levels, but not ridiculously higher. They're in the same order of magnitude. And in point of fact, it's about the ratio of the mobility difference between the holes and electrons. So that's pretty much what you'd expect from UN and UP. The mobilities of the holes and electrons being in normal sort of 2 to 2.5 to 1 ratio or 3 to 1 ratio, that would pretty well account for the difference here in these threshold current levels. One thing that jumps out at you right away with respect to the nFET characteristics is although there should be a factor of 6 difference in currents based on the differences in the strength ratio for each of these curves, and indeed you see about a factor of 6 difference up here when the devices are on hard, maybe a little bit more than 6 for the pFETs. For the nFET devices, you don't get that constant factor of 6 all the way through. It seems that the threshold voltage in the models of the nFETs have been tuned in such a way that the weak inversion part of the curves all tend to be collapsed almost on top of each other. Not quite on top of each other, but they're certainly much, much less than a factor of 6. It's maybe more like a factor of 1.5. So one take-home message from that right away is that if you're hoping to use a strength ratio adjustment by making a transistor longer and the currents are in weak inversion, you're not going to get nearly the ratio that you expect based on making the length ratio be a certain value. So if you want to get a factor of 6 down in current by lengthening a transistor by a factor of 6, and that current happens to be, let's say, below a microamp, you're going to be very sorely disappointed. So that's something to keep in mind. You should be able to connect unit devices in series or in parallel and get a straight-up multiplication, I would expect, but you're not going to do it by just making the transistor longer or shorter. So, moral of the story is follow the unit matching principle. As for the general shape of the curve, the shapes of the curve are pretty well captured by the simple EKV model. You can see that it sort of underestimates the current here in moderate inversion and then overestimates the current up here when you start to get mobility reduction and velocity saturation kicking in at the higher current levels. But it does a pretty credible job. It captures a transition from weak inversion to strong inversion quite nicely. That suggests to me that an EKV 2.6 model set of parameters could be developed for these devices that would do a very reasonable job for the nFETs. The pFET characteristics are a little funky. We do get them being parallel here all the way through, which is what you'd expect if the current scales inversely with the length of the transistors. But we got some funny shape to this curve here, which I don't quite understand. So it looks like there's kind of a dip in the curve here in the range of maybe 10 nanoamps to 1 microamp. And then we've got this kink in the curve down here below, I don't know, about a nanoamp or maybe 500 picoamps that causes the current to deviate from what you would expect based on sort of a fit to the curve up here in the transition region. So I really have no idea what's going on with that, and that suggests that the simple EKV model isn't going to do a really great job here. So I'm not sure if this is an artifact of the model or if this is what the devices really look like down in weak inversion. It would be nice to know. I don't know if this dip here is real or whether it's just a poorly tuned set of model parameters in the PDK. Anyway, so that's the shape of the gate characteristics. Now, if you take those curves and take the partial derivative or an approximation of the partial derivative of those curves, you get the transconductance gain. And we can plot that as a function of the saturation current. And the EKV model actually does quite a credible job until you get up here to where you start to get the bending over here, probably due to mobility reduction and carrier velocity saturation eventually. So this is probably carrier velocity saturation up here. And so that will start to flatten this curve out. But it does capture this behavior quite nicely through the weak inversion to moderate inversion to strong inversion. Very nicely with the fit parameters from the curves on the previous page. And this is the EKV formula for the transconductance gain for the simplified 3-parameter EKV model that is being used to fit these curves with the same parameters as the gate characteristics. Same is true for the pFETs, although because of the sort of kink in the curve, you do get a little bit of deviation down here at these low currents where the curve was departing from the prediction from the EKV model. You still get roughly translinear behavior. It's not terrible, and you get this little wiggle up here, which is probably correlating with the little hollow in the curve. But overall, it does a pretty credible job at capturing the behavior of the transconductance gain as a function of current. This is some data that's meant to summarize a bunch of drain characteristics over a bunch of different transistors with all of width 3 microns and various channel lengths from minimum length of 0.15 microns all the way up, in this case, to 6 microns. And this is a plot of the intrinsic gain, GS times RO, expressed in decibels as a function of saturation current level. So I'm extracting this from a drain curve by fitting the IV curve with a straight line down deep in the ohmic region. Would sometimes be called the on conductance of the transistor deep in the ohmic region. That turns out to be exactly equal to the source conductance, incremental source conductance of the transistor when it's operating in saturation. So we can use that as a proxy or a direct measure of the source conductance. And then the reciprocal of the slope of the best fit line to the saturation region would be the output resistance, RO, due to channel length modulation or drain-induced barrier lowering or a combination of the two. And so the product of those is the intrinsic gain, or one of the intrinsic gains of the transistor. And so that's a useful measure for how much gain we can expect to get out of a single-stage amplifier, and also a measure of how flat the drain characteristics are in saturation. The higher this number, the flatter the drain characteristics. And so here we see a general progression from relatively poor intrinsic gain of only maybe 16 or 17 dBs down here for the minimum length device. Gets much better starting at maybe half a micron. The funny thing about these nFETs is that it seems like they are all on top of each other here. So you can go from something that's only maybe about a little more than 3 times the minimum channel length up to something that's well over 10 times the minimum channel length here. And you don't get very much increase in the intrinsic gain of the transistor. That's really strange. And then when you get up here, you start to get an increase again at 3, 4, 5. And I'm not sure if this is an artifact of the binning of the transistor models. And so in this particular range of channel lengths, we get this kind of compression of the curves together. But this is quite unusual and quite surprising. And the other thing that's quite surprising is that for a device that's 6 microns long in this technology, which is, let's see, that would be 1.5 microns would be 10 times minimum channel length. So this would be 40 times minimum channel length. The intrinsic gain of these transistors is only 50 dBs, which is, less than a factor of 1,000, which is really, really strange. I would not expect that for devices that are this much longer than the minimum channel length. So that's something to be aware of. So for the NMOS transistors, you're going to have a hard time making a current source without doing things like cascoding or using regulated cascodes, even if you use pretty long channel lengths. So you're not going to do very well using something like, a half micron channel length. And you're certainly not going to do any much better by going up to 2 microns here. The marginal improvement you get by increasing the channel length from 0.5 to 2 is almost negligible. And so I guess if you have to use, if you're able to get away with using something with an intrinsic gain in this band, I guess the message here is you go with a 0.5 micron channel length. You don't go with a 2 micron channel length. But then you pay through the nose if you want to get up to 50 dBs in terms of going from 0.5 to 6 microns. So that's the intrinsic gain of the NMOS transistors. This is the intrinsic gain for the PMOS transistors. Here you see a different story. Here my channel lengths run from 0.15 microns up only to 3 microns. So I'm going 0.15, 0.25, 0.5, 0.6, 0.75, 1, 1.5, 2, and 3. So on the previous slide we went up to 6 microns. Here we're going up to 3. And whereas with the NMOS transistors at 6 microns, we were only down at 50 dBs here. At half that length, we're almost up to 70 dBs of intrinsic gain with the PMOS transistors. So the PMOS transistors behave much more like I would expect in terms of their intrinsic gains, where you continue to get a good increase here without this kind of pause in the middle. You'll get really nice flat output characteristics with the PMOS transistors. So that may mean things like where you would have had to cascode an NMOS transistor in order to get a good current source. With a PMOS current source, you might just be able to get away with making the transistor a little bit longer and not cascoding. So that's something to keep in mind when designing with these pFETs. So another measure of kind of how flat the output characteristics is here is 1 over what I'm calling 1 over the early voltage. This actually works out to be sort of the per unit increase in current in the saturation region per volt. So it's per unit increase in current per volt, and that turns out to be 1 over the early voltage. This would also be the channel length modulation parameter in normal simple MOSFET models in SPICE. It's sometimes called lambda. But for the NMOS transistors, we again see this sort of compression and this sort of only marginal improvement as you increase the channel length over quite a range from 0.5 to 6 microns. So what this is saying is that for the minimum channel length device, deep and weak inversion, and there's lots of dibble in the output characteristics for this 0.15 micron device, the current increases by a factor of 4. So that's 400% per volt as you increase the drain voltage. So that's an enormous increase. But then when you get down to 0.5 microns, the current increases by about 20% here, maybe 18% per volt as you increase the drain voltage. And then there's this compression here where it doesn't really get any better at all for 1 micron and then for 2 microns. And it starts to decrease marginally for 3 microns up to 6 microns. So, but even at 6 microns, the increase in current is still more than 10% per volt, which is really surprising. Okay. What you'd expect to see is that this continues to go down so that you might only get like a 1% per volt increase in current, which would be this 10 milli mark down here. But you don't start getting that until you get up here to in strong inversion. And at that point, at that point, you're down here. But through the weak inversion region, this is very surprising. Again, the story is a bit different for the PMOS transistors. So you have a worse increase for the minimum length device, but by the time you get up to 3 microns, you're down at the 1% per volt level pretty much. So again, with the PMOS transistors, you do continue to get good improvement in the flatness of the output characteristics and saturation as you increase the channel length. So that says that you can buy additional flatness by increasing the length for the PMOS transistors. So the last slide I have here is a summary of a bunch of Monte Carlo simulations that I ran with a bunch of different device sizes. And so what I'm showing you here is a plot of the coefficient of variation of the current. So this is the standard deviation of the current divided by the mean of the current. So it's a per unit variation in the current. And I've got two different kinds of point markers here. I've got the circles, and I'm calling this the strong inversion mismatch. And I've got the pluses, which is the weak inversion mismatch. And technically the difference between these two things is that this is the specific current in the EKV model, and this is what you would get up in strong inversion for the current mismatch once the effective threshold voltage mismatch has sort of been diluted by the gate to source voltage of the device. And so this is kind of like the best case matching. And then this cluster of points up here would represent the combined effect of the IS mismatch and the threshold voltage mismatch and the subthreshold slope mismatch. And so this is kind of the worst case variation here. And so calling this weak inversion mismatch and strong inversion mismatch. And a couple of things you'll notice here. So these lines here are the ideal sort of Pelgrim's rule, Pelgrim's model for mismatch, where the coefficient of variation scales inversely with the square root of the area of the device. So this is the coefficient of variation plotted as a function of area on a log-log scale, which turns an inverse square root relationship into a straight line with a slope of -1/2, which you can see here. We go down 1 order of magnitude in the vertical axis for 2 orders of magnitude increase in the horizontal axis. So that's a slope of -1/2. And you can see that the general trend here is to be parallel to these Pelgrim's rule lines. So they do follow Pelgrim's rule, which is, I guess, to be expected given that's how the mismatch is modeled in the PDK. Although the parameters that are actually varied in the PDK are not directly the parameters that I'm reporting on here. So these even though they're combining the effects of several other variations, still follow Pelgrim's rule generally. We can see that there isn't any clear distinction between the NMOS and the PMOS up here. It seems like in weak inversion the mismatch is just about the same for both types of devices. But down here for the strong inversion mismatch, it seems like the pFETs are systematically better matched than the nFETs are, at least according to the mismatch models in the PDK. You can get a sense for how big you need to make the devices to achieve a certain level of mismatch from a plot like this. So to get a coefficient of variation of 1%, which would be the 10 milli line here, you kind of have to get up into kind of the 1 to 10 square micron range for the pFETs, and for the nFETs you have to be in the sort of above probably 7 square microns or so for the nFETs. And to get into the 10% range for weak inversion, you have to make them kind of in this kind of 10 square microns or larger range. Okay. So I should say each point on this curve, or each point on this plot, represents statistics drawn from 100 Monte Carlo simulations and 100 curve fits to the kind of gate characteristics that I showed on the first slide. So there's a lot of simulations that went into generating this plot. And I guess that's about all I will say about that. I did want to show you some drain characteristics to give you a sense for what those look like in this technology. And so in order to do that, I'm just going to use my Python data plotting environment and just kind of step through some plots of characteristics. And we'll do the 3 by 0.5 first. And I want to make a figure. And I want to configure it. Oops. That's what I get for trying to do this live. I need to put one more close in there. There we go. Okay, so here we are down at a 1 picoamp of saturation current roughly, and you can see the size of the increase in the current through the saturation region. And as we continue to increase higher current levels, you can see that this is not changing by very much. It relatively stays the same, and it will start to flatten out when we get up into the kind of hundreds of nanoamps. So this is, we're moving into the strong inversion region where the early effect gets less and less. And that's where we are at 100 microamps. So we still get a pretty significant increase in the current here from maybe, I don't know, 90 microamps here up to maybe 105 microamps. So that's, you know, a 15% increase in the current roughly. So that's a half micron channel length. So if I, instead of doing the half micron one, I load in the 3x3, and we do the same thing. Here we are at a picoamp. It's still looking like a pretty large increase in the current. Right, that's a fairly comparable increase to the current as we saw with the half micron long one. And in the hundreds of nanoamps, it starts to get a little bit flatter. And here, it's flattened out by quite a bit, but we're a bit further above threshold because of the factor of 6 difference in the channel length. At 100 microamps, it takes being up higher in strong inversion to get to that current level. And you can see that by the fact that it takes us almost 0.8 of a volt here to saturate the transistor. Okay, that's the nFET characteristics. I wonder if I can load the pFET ones from here without having to go out. So let's try that. Let's try this. Load workspace and then // pMOSCare, and we'll do pdrain 3x05.lab. Hey, it worked. So let's see what we got. So these are the PMOSs. This is the half micron. And you can see that we still get a pretty good increase in the percentage increase in the current here down in weak inversion. But you can see it's starting to flatten out even at the hundreds of picoamp current levels and the early nanoamp levels. And by the time we're up to the hundreds of nanoamps, we actually have much of a less of an increase than we had with the NMOS at this channel length. And so this is much flatter than the NMOS was in strong inversion. Here, this may be going from like maybe 95 to 100, just over 100 here, between, say, 0.8 volts and 1.8 volts. So the PMOS characteristic here is quite a lot flatter at the half micron length. Let's see what the 3 micron long one looks like. Now that's much flatter than the NMOS. Here at 10 picoamps of saturation current, that's, maybe a 3% increase in the current over the entire 0.1 to 1.8 volt range. And you can see these curves are just beautiful in terms of how flat they are. And that's a consistent story all the way through. And now you can see here, with the PMOS transistors, we are way above threshold. So you're almost not even to saturation by the time you get up to the full power supply, when we're up to 100 microamps. So that's also something to keep in mind. You have to make the transistors wider, so the unit aspect ratio doesn't really get you into saturation at all when you're up at the 100 microamp current level. You have to make the devices a lot wider. So that's it. Hope that was a helpful summary of the transistor characteristics. I will make my plots available for download from the course website if you want to take a look at those plots in more detail. Anyway, thanks for watching.